We'll now discuss the phenomena of what happens if malloc fails to allocate memory, right? And let's go back and discuss or paint a picture of what should happen for malloc to fail, right? For malloc to fail, the number of bytes that you ask should be greater than what's available in the heap, right? That's the only condition I know at least wherein malloc will fail, like the allocation of the memory fails. And so what we are going to do now is take our previous program here, modify it a little bit such that we push malloc towards failure, right? So as part of that, what we are going to do is ask malloc to give us more and more um, on every run essentially, right? So let me then go ahead, get this out of the way, and instead of 400 bytes, let's ask it for maybe 4 MB. How about that, right? So, and this number here, this is 4, this makes it 1K. Well, 1K into 4 is 4K, and this should have been 4. When we multiply it by 1024 again, this will convert into MB. So what we are going to now do is ask malloc for 4 MB worth of what do you say 4 MB bytes, and let's see if malloc fails. And what happens? Well, first off, let's say if malloc fails, then the question is what does it return? Because how does it convey essentially that it failed? And the answer to that is it simply returns this. And this, if from previous videos we called was the value null, right? So when malloc fails, it returns a null. As a result of that, P would be pointing to memory location 0, right? That's what it means to be a null pointer. So essentially P would become a null pointer. So what we are going to do is we are going to get rid of these statements and only print the address that P is holding. And the moment P is holding 0, we would know that malloc has failed. So let's go ahead and uh, essentially modify our program here. So I'll make this 4, and let's get rid of maybe all of this. And what I'll do is put a %p here, and know that we don't want to dereference p anymore. We don't want value that p is pointing to. In the sense, the contents of the memory that p is pointing to, we don't want that. What we want is what address is p holding, and to do that we get rid of the star or the asterisk, and so we are then left with this. All right, let's go ahead, compile and run the code. Fair, p is having some value. What we are now going to do is maybe okay, let me do one more thing, which is just so that life is easy. I'll just say um, okay, request. Our request is this, and let me take this macro and put it here. So essentially, this keyword would be replaced by this arithmetic operation. So we were asking for 4 MB. Let's notch it up and ask for maybe I don't know, 4 GB. This will definitely fail, hopefully. Uh, Never know if malloc succeeds. Uh, well, what does it say? Int results in 0. Ooh, okay. So what's happening here is we are hitting essentially the limits of the value that malloc can take in. Let me go ahead and quickly show you what I mean. So malloc would take size underscore t size and size underscore t behind the scenes. So okay, this looks very cryptic, but this behind the scene is I think it's an unsigned integer. Most likely this is an unsigned int, and I'm saying most likely it's an unsigned int just because I have some background experience, and over time I figured that size underscore t is essentially the size of the standard integer that the machine supports. So we won't be able to ask it for 4 GB. Let's um, um, let's try 2 GB. So let's make it 2 here, and let's see if this compiles. Mm, by the way, another thing, you should notice this warning also, which is, it's saying, hey, the overflow is expression of type int results in a 0, right? Okay, so most likely size underscore t was equal to int behind the scene. Size underscore t is not a standard C thing. It's just a type def or some sort of a macro of this nature. Right? All right. So we're asking for 2 GB now. Let's go ahead and compile this. Didn't work. Nice. And now it's telling us that something, something, something. Let's ask it for 1 GB. Let's see. All right, 1 GB, no warnings there. Let's try and run. Okay, it still gave us something, which is interesting. Uh, so 1 GB it is able to allocate. How do we push it to failure? Okay, let's do this then. Let's put on a for loop here. hmm And we are going to do something which is forbidden. Um, but let's do it because why not? So I'll take this, put it here. We don't want to assign p anything just yet. And what we'll then do is we'll say p equals same story, malloc the request, and let's not call free, which has its own, we are essentially committing a crime here. But to push malloc to failure, let's just keep on asking it for memory and never return the memory back. And also the crime that we are committing, let's talk about that. And maybe before that, let's reclaim our screen real estate. Okay. So what we are now saying is somewhere there is P, right? And somewhere there is a heap. So we are asking that, hey, give us some 1 GB from the heap. So let's say this is the address ABC, right? So initially there would be ABC here on the first malloc. Next time around, we allocate more 1 GB, right? And what we are saying is, oh, put that address in P. So this might again be, let's say, A, C, D, some zeros, right? So we are saying, okay, scratch this, and then, you know, put this here. So what you should notice is we have lost the pointer to this first GB, right? So this space was allocated, and now there is no, what do you say, no chance that we will be able to ever free it because we have lost track of what was the starting pointer, starting memory location where that initial 1 GB was allocated. Because our P now is holding this value. So we have lost track of this, right? And this is, well, one of the things which is we have leaked memory. Memory, the heap allocator, the algorithm can never go back and be like, oh, this is a free region, because we essentially lost track of it and we never called free on it. In fact, what we are doing here is on a recursion basis, or in a loop, we are allocating 1 GB to see what is the limit of the heap. And once we have hit the limit of the heap, hopefully malloc returns back a null and p is printed as nil or 0. Right. Okay, let's then go ahead and commit the crime of requesting 10 GB, and let me also then go ahead and print the iteration count. There's a dog in the background, so Okay, let's go ahead and compile. Compile fine. Still gave us the memories that we required. Interestingly, is it? Hmm, nice. So let's make this 100. Hopefully it fails. And if I have not succeeded in breaking it, also there is a error here. Nice. Um, oh, actually, percent I is not required. Yeah, this is correct. Compile, rerun. Wow, it's still allocated. Hmm, interesting. 1000 times? How much memory does the system have? Come on. Uh, uh, nope, still not failing. I don't know how many GBs this. I'm wondering if there is a trick behind the scene that the operating system is playing. Uh, nope, still doesn't. Nice. This is an interesting experiment. What I'm imagining might be happening is that because we are on a virtual machine, maybe behind the scene it just goes on extending the nice, finally, you know, okay. So if you see nil here, and I don't know when the nil came, so let's go ahead and make a check here. Uh, if p equals null, then break or return with -1, right? So mhm, hopefully it fails. Come on, nice. Okay, so at least at this point, on some, what is that? 1,30,000. Oh wow, 131,061. It has failed on that iteration, which is a bit bizarre and uncomfortable for me. But nonetheless, we got to a point um, where the malloc failed to allocate the memory that we required, and then as a result of that, it returned a null pointer. So as part of this lecture, this video, I just wanted to convince you that the malloc failure would result in a null pointer being returned. And along the way, what we have done is we have committed crime, which is allocated a lot of memory and never freed it, right? And that's something that we call memory leak, which is the heap would be unaware that there is an unused memory chunk, um, and pretty bad thing to do. Well, here, if you're wondering why it took so many iterations before we could get it to the point of failure, I suppose behind the scenes some sort of uh, virtual memory related things are happening. I'm not quite sure on that, so I need to do my homework. But hopefully, this is also a challenge for you to go research something about virtual memory and memory allocation.